Yeah, so in this video, I'll be sharing my recent work of policy evaluation for large action spaces via embeddings, which is going to be presented at this year's ICML conference. And this is a joint work with my PhD advisor, Thorsten, at Cornell University. So I'm going to start off by formulating the standard of policy evaluation for the contextual bandit setting. And then I'm going to illustrate some of the critical issues of the existing estimators, especially for large action spaces. So simply speaking, the typical importance weighting approach is going to be very inaccurate when it is applied to the growing number of action, which is actually very realistic in the industrial application of policy evaluation. So to deal with the large action spaces, I'm going to propose a new framework and a new estimator, leveraging some actual embedding observations, right? So our high-level key idea is to utilize auxiliary information about the action, maybe some actual features for performing much more accurate policy evaluation, even for large action spaces. And there's some interesting empirical results about the proposed estimator at the end of the video. So at a high level, the policy evaluation is about the performance evaluation of the automated decision-making algorithm like contextual bandits or reinforcement learning. So the canonical example is item recommendation or some product recommendation. And the goal is to maximize some notion of reward rather than making some accurate prediction. So there are many applications of automated decision making, from like YouTube recommendation to like movie recommendation. So there are many papers talking about how to improve the decision making quality, like contextual bandits or like offline reinforcement learning. But the motivation of policy evaluation is a little bit different, right? It's more like a statistical estimation problem. And the important question in policy evaluation is like, how can we evaluate the performance of some new decision making policy by using only the historical log data collected by a different policy, or the login policy or past policy. So there are many papers or growing number of papers also talking about how to do policy evaluation or accurate policy evaluation using only the historical log bandit data. But the thing is that it's still very difficult to deal with large action spaces in policy evaluation, right? So in this kind of industrial applications or like the realistic situations of policy evaluation, we often have to deal with a large number of actions, right? Thousands or millions or even more number of actions. But given the existing literature, actually, it's going to be very difficult to do a practical policy evaluation for large action spaces. So our high-level research motivation is to to make it possible to do much more accurate policy evaluation, even for large action spaces, right? So that's our high-level kind of the specific research motivation in the paper. But before going into the research detail, let me formulate the policy evaluation for the contextual bandit setting. So here is the kind of the general common data generated process considered in policy evaluation. So we first observe some context X from the unknown distribution PX, some user information. And then the login policy by now stochastically picks an action A. So this is like a stochastic movie recommendation or some product recommendation. And we finally observe some reward from the unknown condition distribution given context X and action A, right? So reward can be clicks or conversions or some revenue. So the login policy interacts with the environment and produces the log data, the collection of context and an action and reward, which is very useful for performing policy evaluation. The goal of policy evaluation is to accurately estimate the value or the performance of some evaluation policy or the new policy. So the value or the performance of an evaluation policy, which is our estimate, is commonly defined as the expected reward we get when we kind of hypothetically implement the evaluation policy in the environment. So of course, we don't want to actually implement the evaluation policy, or we don't want to implement the online experiment, which might be risky. So let's estimate this value of evaluation policy using only the historical log data. That's the goal of policy evaluation. So technically, we want to develop an accurate estimator for policy evaluation. So an estimator tries to statistically approximate our estimate using only the log bandit data given by the login policy, but the login policy is different from the evaluation policy. So in building a new estimator, we have to deal with the distribution shift between the evaluation policy and the login policy. So an accuracy of an estimator is often quantified by MIPS, which can be decomposed into the square bias and the variance. So in order to achieve a small MSE, bias and variance are equally important, right? So sometimes we want to sacrifice the bias a little bit to get a sufficient amount of bias extraction. But anyway, the most important basic estimator in policy evaluation is the IPS estimator or like the important sampling estimator. which uses the importance weighting technique to unbiasedly estimate the policy value using only the historical log data. So here is the definition of IPS, which is very simple. So just a weighted empirical average of the observed reward, and the weight is importance weight, which is just a ratio of the variation policy and the logging policy. So this is very easy to implement, and also there are some nice statistical properties. So this is very popular in practice, and also forms the basis of many recent estimators or like advanced estimators, including WQuest. So the nice property of IPS is the unbiasedness and also the consistency, right? So IPS is unbiased for any evaluation policy, satisfying what is called like the common support assumption. So this assumption is like a verifiable assumption, but requires the logging policy to cover every action that could have taken under the evaluation policy. Otherwise, we don't have information, we don't have any information about the action, some action in the log data. So IPS might have bias. But anyway, under the common support assumption and some identification assumptions, IPS is unbiased and consistent, making it very popular in practice. And also many recent estimators, very recent estimators heavily rely on the IPS estimation technique. But the problem is that IPS is going to be, very inaccurate when we think of applying this framework to large action spaces. So what I'm showing here is just a synthetic illustration of the inaccurate, impractical behavior of IPS in large action spaces. So the y-axis is just MSC, the lower the better, of course. X-axis is the number of actions. So I just increase the number of actions from 10 to 2000, right? So 10 is like the typical policy evaluation experiment, which is a very small scale. 2000 maybe the medium scale, not the large scale, but actually 2000 is like enough to see the inaccurate behavior of IPS. And I think it's already obvious that IPS is getting significantly worse with growing number of actions, which is actually over 10 times worse than the bias baseline, the direct method, in the presence of many actions. And this inaccurate behavior is simply due to the fact that IPS heavily rely on the vanilla importance weight. And the vanilla importance weight was a maximum importance weight is also growing with the growing number of actions, which causes some, the high variance or the unstable estimation problem for the IPS estimator. So IPS is going to be very inaccurate when it is applied to large action spaces. So maybe you might think here that, so why not then using some advanced estimators rather than IPS, like, there's some W-robust or some variants of W-robust to get some variance instruction. Might be a great idea, but the thing is that all these recent estimators still heavily rely on the vanilla importance weighting technique. So they still suffer from a large variance or introduce a lot of bias when they when they modify the importance weight for some variance instruction purpose. So we also illustrated the impractical, inaccurate behavior of these recent estimators. So for example, the W-robust estimator suffers from a very large variance, ends up being very similar to IPS in large action spaces. So there are some other estimators like switch estimator or like the shrinkage estimator, but they actually work almost the same as the biased baseline direct method because they aggressively modify the importance weight for some variance structure purpose, but instead end up losing unbiasedness or consistency, especially in large action spaces. So advanced estimators still have the same issues. They're still using the vanilla importance weight, which is definitely the source of high variance. So our research question is actually pretty simple. We just want to gain a large variance instruction without sacrificing unbiasedness and consistency, even in large action spaces. Actually, some recent papers have kind of similar motivation to get some variance instruction without sacrificing unbiasedness of IPS, but we want to achieve that large variance instruction even in large action spaces, which is actually very difficult given the existing literature. Maybe we need to avoid relying on the vanilla importance weighting anymore, which is definitely the source of high variance. So then how can we do this? So actually, our high-level key idea is pretty simple. We didn't start from thinking about a new estimator, but rather actually we started from reformulating the policy evaluation or the log bandit data. So here is again some arbitrary example of some typical log bandit data, maybe for product recommendation setting. So there's some user context and some action choices by the login policy and some reward, right? So just a log bandit, the typical log bandit data. And our key idea is like, in many situations or like in almost all situations, we should be able to use some additional data about some, some feature of the action space or some additional information in the structure, about the structure of the action space, which we call like the action embeddings or the action features in the paper. So for example, item A might be a book category and a very low price of $20. But the other item, item B, might be a computer category and should be much more expensive, like the $500. In many situations, like, in the movie recommendation or like the music recommendation, we should be able to use this type of action embeddings, right? Maybe some actor information, some category information, some artist information, or maybe we can use also some review comment information or image information as type of action embeddings. So why not leveraging this type of auxiliary information about the structure in the action space, right? Should be able to utilize this type of similarity information for achieving much more accurate policy evaluation, especially in large action spaces. So here is a typical bandit data consistent of, including only some action indices. So should be very difficult to do like, practical policy evaluation with only action indices, especially in large action spaces. So we just additionally assume the observation of the action embeddings, which I'm going to denote by E in the log data. So a bit more formally, we naturally generalize the typical data generative process. I mean, how the log bandit data is generated by just assuming the existence of the action embedding distribution given context X and an action A. And so for given context X and the action choice by the login policy, we additionally observe the action embedding E, which is related to the action A. So this is our data generative process. And actually, there are many ways to construct action embeddings. So maybe the simplest way to construct action embedding is to use the category information. So category information is just a discrete variable and also context independent and deterministic, right? So we're gonna apply the same categorization of the items for every possible context, every possible user. And also there's basically no randomness in the definition of the category information. So this may be the simplest way of, or the simplest type of action embeddings. But we can also think about way, much more general type of action embeddings. Maybe the price information is a great example. So this is a continuous value. And also maybe context dependent and also stochastic. Right? For example, if the price is given by some personalized pricing algorithm running behind the system, then maybe depending on the implementation of the algorithm, the price, this price variable can be context dependent and stochastic. If the pricing algorithm is personalized algorithm and also some stochastic algorithm. But anyway, our the data generating process is very general. We can use basically any type of action embedding, maybe discrete variable, maybe continuous variable. It can even be stochastic. So it should be very natural, right? We should be able to use some type of action features or some action embeddings in many situations. So then the remaining question should be, so how should we utilize action embedding for performing much more accurate policy evaluation, even in large action spaces? So let me just mention here that in this particular research, we assume the existence of some predefined action embeddings, and we focus on analyzing the connection between the quality of the action embeddings and the resulting policy evaluation accuracy. So maybe optimizing or learning action embeddings from the data is one of the very interesting future works. But again, in this video, in this research, let me assume that action embeddings are already given. Let's focus on how to utilize action embeddings and also the statistical properties of the estimator based on the action embeddings. So then to develop a new estimator utilizing or leveraging action embedding observations, I'm going to assume a very useful assumption, which is the no direct effect assumption about the quality of the action embeddings. So this no direct effect assumption is an assumption about the relationship among action and action embedding and the reward, and requires that the every causal effect of the action A on the reward should be fully mediated by the action embedding E, right? So action embeddings should be informative enough to be able to maybe characterize the reward distribution without the action variable A, or maybe in other words, there should not be any direct effect from the action on the reward. So we call this assumption the no direct effect assumption. So from the statistical standpoint, this assumption requires that the action A and the reward should be statistically independent given context X and an action embedding E. Right, so there's no additional information even if you additionally condition on action A, B, or C about the expected reward or the reward distribution, right? If the action embedding is informative enough. So I can also provide a very simple example of the situation where the no direct effect assumption is perfectly satisfied. So here is just a movie recommendation example. There are some movies. The category information, this is just maybe the simplest example of action embedding. Of course, in practice can be multidimensional, can be continuous, but this is just the simplest way of constructing action embeddings in many situations, right? Just a category information. And conversion rate, just an example expected reward function. And given this situation, we see that the action embeddings perfectly, completely explain the variation in the reward function, right? Given the category information, the conversion rate is exactly the same within each category. So given this example, the assumption, the no direct effect assumption is now perfectly true. There's no direct effect from the movie on the conversion rate. It's enough to see the category information or the action embeddings to characterize the conversion rate or the expected reward. And this no direct effect assumption is very useful in the sense that we're going to have a completely new expression of the policy value without using the action variable A under the no direct effect assumption. So here is the value of evaluation policy, our estimate, which is now defined as the expected reward under the evaluation policy. So definitely depends on action variable A because the policy is a distribution over the action space. But under the no direct effect, we can actually specify the value of evaluation policy using only the action embedding observations or the marginal distribution of the action embeddings induced by a particular policy pi rather than the policy pi itself. So marginal distribution of the action embeddings is actually a very, the simple concept. So let me also use a similar example to explain the marginal embedding distribution. So there are some movies, a arbitrary policy, just a recommendation policy, right? 20%, 10%, stuff like that, just a distribution over the action space. And the category information, again, the simplest way of the constructing action embedding, just a simplest example. And given a policy and the embeddings, we see that the marginal distribution of the action embeddings is now very easily defined and calculated. Right, so the marginal distribution is just how frequently we observe each movie category given a particular policy pi. So definitely depend on policy pi. And in this example, we're gonna observe the science fiction movie 40%, and the remaining 60%, we're gonna observe the sports movie. So this is a marginal distribution given policy pi. So this new expression is saying that it's enough to see the category distribution or the marginal embedding distribution given evaluation policy to characterize and specify the value of evaluation policy rather than using the action variable A or the original policy definition or the policy distribution. So based on this new expression of the policy value, I think it's very straightforward to think of what's going to be the proposed estimator utilizing and leveraging action embeddings. Right, so the new expression of policy value actually very straightforwardly naturally leads to the new estimator, which we call the marginal IPS estimator or the MIPS estimator. Right, so here is the definition of our proposed estimator, our main proposal, the MIPS estimator. Looks actually very similar to IPS, right? So this is just a weighted empirical average of the observed reward. But the crucial difference is that the weight is defined completely differently compared to the vanilla imponence weight of IPS. Right, so this is our definition of the imponence weight or the marginal imponence weight, which is now computed over the action embedding space or utilizing the action embedding observations rather than the original action space or just action indices. So the trick we use here is that we just ignore the dependence on the vanilla imponence weight because this is definitely the source of high variance. So we want to achieve a large variance action in large action spaces by maybe ignoring the vanilla imponence weight. And instead, we use the marginal imponence weight using the action embedding observations. So from now, let me formalize some of the nice properties of our proposed MIPS estimator. But roughly speaking, the MIPS estimator is unbiased with alternative assumptions compared to IPS. But the crucial benefit of the MIPS estimator is that we're going to get a large variance action, especially for many number of actions compared to IPS by using the MIPS estimator. So let me first explain the bias analysis about the MIPS estimator. So under the no direct effect assumption, MIPS is unbiased for any evaluation policy satisfying the common embedding support assumption. So the common embedding support assumption is a weaker version of the common support assumption, which is about the embedding space. So this is a weaker assumption because if the common support is true, then the common embedding support assumption is also true, right? So what's nice about the MIPS estimator is that it is unbiased under just a weaker common support assumption. But instead, we need a no direct effect assumption because the MIPS estimator is led by the no direct effect assumption. So maybe one concern here is, so no direct effect assumption may not be true in practice. And also this is an unverifiable assumption from the data. So we also analyze the bias of the MIPS estimator with the violated assumption. I mean, if the no direct effect assumption is not perfectly true, then we're gonna have a bias of the MIPS estimator, which is actually expressed by a very interpretable form. Right, so this is a bias expression under the violated assumption in our bias analysis. And there are actually two decisive factors that characterizes the bias of the MIPS estimator. And the first factor is a kind of the identifiability of the action given the action embeddings. So this is the conditional distribution of the action given action embeddings. So if action embeddings are like the very informative, maybe high dimensional, then it should be very easy to identify an action A that is explained by action embedding E. Then this conditional distribution should be near deterministic, meaning that the first factor is going to be, it's going to be close to zero, meaning that the bias of the MIPS estimator is also going to be very small. Right, so this roughly speaking, the first factor is roughly saying that the action embeddings should be as informative as possible to reduce the bias of the MIPS estimator, even if the no direct effect assumption is not perfectly true. The second factor is more about the satisfaction of the no direct effect assumption. So this is the amount of direct effect that is not mediated by the action embedding E or the given action embedding E. Right, so if the no direct effect assumption is perfectly true, then the second factor is actually zero. So this also saying that action embedding should be as informative as possible to reduce the bias, even if the no direct effect assumption is not perfectly true, right? It's too important to try to mediate as much direct effect as possible, even if the assumption is not perfectly true. So this is our bias analysis under the violated assumption. But to summarize a bit, the MIPS estimator is unbiased with a one weaker assumption and a one additional assumption. I mean the no direct effect assumption. So basically, the MIPS estimator retains a nice property of the IPS estimator, and we did discuss the bias of the MIPS estimator under the violated assumption. And it's still important to try to use the informative action embeddings, maybe high dimensional action embeddings, even if we cannot satisfy the no direct effect assumption perfectly. So this is a bias analysis. And then the crucial benefit of the MIPS estimator is the variance reduction property compared to IPS. So what we did in the variance analysis is actually very simple. So we just compare the variance of IPS with that of the MIPS estimator. And we derived a very interpretable and simple variance reduction formula consisting of the second moment of the reward and the variance of the vanilla impedance weight, which is always non-negative. So the first insight from this variance reduction formula is that the variance of the proposed estimator, the MIPS estimator, is never worse than the variance of the IPS estimator because this is always non-negative. And the most promising insight from this variance reduction formula is that we're gonna get, or we should get a large variance reduction, especially for larger action spaces, because this is the variance of the vanilla impedance weight, and the vanilla impedance weight should have a high variance or higher variance if there are many number of actions or larger number of actions in the action space. With that, I mean, this actually suggests that the MIPS estimator is increasingly favorable. It's a very promising solution for large action spaces because we're gonna get a larger variance action compared to IPS for large action spaces. So that's a crucial benefit of the MIPS estimator in terms of the variance reduction. But maybe another very interesting insight we get from this variance reduction formula is that this actually saying that the action embeddings should not be so informative. Well, maybe in other words, this conditional distribution of the action given action embeddings should be sufficiently stochastic to get a sufficient amount of variance reduction, right? So this variance is actually defined with respect to the conditional distribution of the action given action embeddings, which also appeared in the bias analysis. So if the action embeddings are like the overly informative, then this conditional distribution is going to be nearly deterministic, meaning that this variance reduction formula it's going to be close to 0. So to get a variance reduction, to get a sufficient amount of variance reduction, we actually control or limit the information included in the actual image. So actual image should not be so informative in terms of the variance reduction perspective. So this is actually the opposite, the completely the opposite motivation compared to what we had in the bias reduction analysis, right? So to summarize the variance trade-off of the MIPS estimator, so to reduce the bias or to be unbiased, we should actually use informative action embeddings, maybe high dimensional, high cardinality type of action embeddings, maybe to satisfy the no direct effect assumption perfectly. But to reduce the variance, which is also very important, we should actually use the opposite, the cursor noisy type of action embeddings, limited information, maybe low dimensional, low cardinality type of action embeddings to get a large variance reduction compared to IPS. So maybe the very interesting insight we got from the statistical analysis of the MIPS estimator is that the bias variance trade-off of the MIPS estimator is now controlled by the informativeness or the expressiveness of the action embeddings. And which also implies that we don't have to care too much about the satisfaction of the no direct effect assumption, right? Because the no direct effect assumption is only necessary for unbiasedness. But in order to achieve in a small MSE, we also have to care about the variance reduction. And to reduce the variance, we should actually use cursor noise action embeddings, meaning that sometimes we actually violate the no direct effect assumption to limit the information included in the action embeddings to get a sufficient amount of variance reduction. Right, so maybe the no direct effect assumption is a very critical point of the MIPS estimator. So the easiest or the simplest criticism anyone can immediately make about the MIPS estimator is a no direct effect assumption, which might be strong, which might be unverifiable in practice. But actually, it turned out that we don't have to care too much about the satisfaction of the no direct effect. Rather, we have to control the satisfaction of the no direct effect to further improve the MSE of the MIPS estimator, because MSE is a bias plus the variance, and you have to also care about the variance reduction. There are actually some interesting empirical results in the experiment section, suggesting that the MIPS estimator is optimal in terms of MSE if we violate the no direct effect assumption a little bit. Right, but anyway, to summarize the technical section, so our initial motivation came from the fact that the IPS and many other estimators based on IPS become actually very inaccurate and impractical with growing number of actions, right? Mainly due to the high variance. So our high-level key idea is to assume the auxiliary knowledge or the supplemental data about the actions in the form of action embeddings. And we propose the MIPS estimator based on the no direct effect assumption as kind of a useful or starting motivating assumption. And we characterize the bias and variance of the MIPS estimator, actually implying a very interesting bias variance trade-off in terms of the quality of the actual embeddings. And in order to achieve a small MSE, sometimes we actually should violate the no direct effect assumption rather than overly pursuing the satisfaction of the no direct effect assumption. So finally, I'm going to introduce some of the interesting synthetic experiment results. So there are some baseline estimators, direct method, IPS, and W-robust. Actually, we compared many other baseline estimators in the paper. So if you're interested in additional experiment results, please also look at the paper. There are like two types of MIPS, one with the estimated importance weight and the other one with the true importance weight, which provides the best achievable accuracy given the high-level MIPS framework. There are some basic experiment configurations, but I just want to highlight here that our experiment setting is much more large scale compared to the small scale experiment, the typical experiment done in many previous OPE papers. So maybe the most basic important comparison is the increase in number of actions. So I just compare the baseline estimators with the proposed MIPS estimator in the growing number of actions. So y-axis is MSE, the lower the better. The x-axis is the number of action. I just increase the number of action from 10 to 5,000. And we observe that the IPS and the W-robust is very inaccurate, become very inaccurate in the presence of many actions. But our proposed estimator, the MIPS estimator, actually much more robust to the growing number of actions, and actually over 10 times better, especially for large number of actions. And our estimator is also consistently better than direct method, achieving large variance action, especially for large action spaces. So another important the experiment setting is increasing number of data. And this time we observed that the MIPS estimator, the proposed estimator, converged to the true positive value, and actually much faster than the IPS and W bust. So IPS and W bust also converge to true positive value, but the convergence is very slow in the presence of many actions. So another baseline is direct method, but it is highly biased even if we increase the data. So the MIPS estimator is increasingly better than direct method when we increase the number of data. So the MIPS estimator avoids sacrificing consistency and also unbiasedness. So to summarize, the MIPS estimator is a much more robust growing action set compared to IPS and W robust, and also make free use of large data and converge much faster than IPS and W robust. So MIPS dominates direct method, IPS, W robust, and actually many other estimators for both crucial cases. So maybe, but the most interesting kind of or surprising experiment result is like how robust the MIPS can be for the bio-related assumption. So to see the robustness, we synthesize kind of the 20-dimension synthetic action embeddings, and all 20 dimensions are necessary to satisfy the no direct effect assumption. And to see the robustness, we gradually drop some necessary embedding dimensions from the off-base evaluation process. So this time the x-axis is the number of unobserved or missing embedding dimensions. So 0 means that the no direct effect assumption is perfectly true and the MIPS estimator is unbiased. But 18 means that most of the embedding dimensions are unfortunately missing. And actually, we observe a very surprising or interesting result, suggesting that actually dropping some embedding dimensions, minimizing the MSE of the proposed MIPS estimator. So this actually suggests that we don't have to satisfy the no direct effect assumption in terms of MSE. So we don't have to overly care about the satisfaction of the no direct effect, but rather we want to control the satisfaction of the no direct effect to further improve the MSE of the MIPS estimator. And this interesting phenomenon is completely due to the bias-variance trade-off. So as suggested in our bias analysis, so missing embedding dimensions introduces some bias, which is consistent with our bias analysis. But at the same time, the variance decreases with the missing dimensions, which is also consistent with our variance analysis. So rather than overly sensitive, rather than being overly sensitive to the satisfaction of the no direct effect, we should maybe control the bias-variance trade-off based on the satisfaction of the no direct effect, or maybe sometimes it's effective to strategically violate the no direct effect to reduce the variance and to improve the MSE of the resulting estimator. We did discuss how to data-drivenly select which embedding dimensions to include or drop from the estimation process, but this is based on the existing method for hyperparameter tuning of voice evaluation. So if you're interested, please also look at the experiment section of the paper about the data-driven embedding selection method. I just want to finally highlight that there are some other practical benefits of the MIPS estimator. So in addition to the robustness to the growing number of actions, MIPS is also more robust to deterministic evaluation policies and also robust to the noisy rewards compared to IPS and W robust. So actually, the MIPS is very useful in many practical and challenging situations like large action spaces, deterministic evaluation policies, and also the noisy environment. But anyway, to summarize the empirical results, with growing number of actions, MIPS provides a large variance reduction compared to IPS and W robust, and works even better than the biased baseline direct method. And then with growing sample size, MIPS actually works like an unbiased and consistent estimator and converge to the true positive value much faster than IPS and W robust in the presence of many actions. And even if we violate the no direct effect assumption and introduce some bias, intentionally or strategically dropping some embedding dimensions actually provides some great MSE gain because it actually provides a sufficient or like the larger variance action. So the no direct effect assumption is not the type of assumption we must satisfy, but rather the type of assumption we want to control, right? We want to control the satisfaction of the no direct effect to further improve the MSE. The bias and variance are equally important. So all these empirical results actually suggest a very promising potential of the high-level MIPS framework, right? So the MIPS framework is very general. So many other estimators, many other recent estimators that depend on IPS can be actually very easily improved by just applying the high-level MIPS framework rather than the IPS. So that's basically the end of the video. I just want to finally mention that we implemented the MIPS estimator in the Open Bandit pipeline package, which is a open source Python package for off-voice evaluation. So if you're interested in using our MIPS estimator in your practice, in your research, please also look at the Open Bandit pipeline, which is available on a GitHub repository. So thank you for your interest.